Okay. We are thank you all for coming for today's seminar, and it's my great pleasure to welcome Dr. Junjie Yao from Duke University. I know Junjie for a very very long time, back when we were both like postdoc many years ago, and um, I don't want to read the bio, but I know him pretty well. He got his PhD from Washington St. Louis with Dr. Nihong Wang. I believe he also did a very short period of postdoc with him, and he started the independent lab at Duke University, and now he's a tenured professor there. I think 2 or 3 years ago, right? Um, he is also like a chaired professor there, and he is associate director for photonics at Duke. Um, and Junjie is doing some wonderful research on photoacoustic imaging, but more than that, he actually developed some new directions like diffraction ultrasound and even detecting the bubble during the um, can people hear this? Yeah. Okay. Yeah. So some new directions you guys were seeing in the presentation today, um, and his research is highly cited. He's very young, but his citation is up to 15,000 already. So wonderful. Very impressive. He has been published papers on some really high-profile journal like Science, Nature, many of those. And he's very active in the community. He's associate editor for Science Advance, Photoacoustics, many other journals. He has been awarded for from many organizations, right, including NSF Career Award, um, and he is already fellow for many societies, including Optica, SPIE, AIBME. So it's absolutely. We used to say Junjie was a rising star. Now he's not a rising star. He is the star, and he's really shining in the field. So with that, I can stop here. Please join me. Welcome Junjie for the talk.
Okay. Thank you, Xiang, and thank you for inviting me here. Enjoy your food, and don't let me stop your lunch. And Xiang is right. We know each other since we were both postdocs, and in some ways, I still feel I'm a postdoc while Xiang is already a professor. So that's a difference between us. And well, this is not first time I came to UCI, but this is the first time for me to be at our Beckman Institute, a laser institute. As Xiang mentioned, I'm also the associate director for a similar institute at Duke. It's called Fitzpatrick Institute for Photonics. And so I'm familiar with the process. And so feel free to interact while you enjoy your lunch. Feel free to ask questions, and I'll do my best to entertain you while you're eating. I do have a few work that is not just on light. We also try to use ultrasound throughout my research to help us. I will show you 3 major directions we're working on right now, and some are funded, some are not really funded. I mean, hopefully we can do more work even it's not funded. But I just want to interact with you guys with ideas. So hopefully we can find something to work together from here. And let's just keep going here. So this is I have a small startup which commercialize my technologies in the lab. Actually, Luminous Imaging is moving to the Bay Area this month, so they got some funding from the investors here. And that's my lab during the pandemic, and it's more or less the same size. I also want to acknowledge my collaborators all over the country, and we also have some Xiao Yu, who is not here right now, but we're working together on some spatial omics work. So very happy to work with those wonderful collaborators. Without them, this is not possible. All right, so for us, in case you have never been to Duke, I took a really short walk this morning after my breakfast. I feel you guys are more vivid. You have all different kinds of veggies around. We only have trees, so we don't have too much flowers. That's North Carolina. It's almost feel like you carve a space in the woods. So we are trees everywhere, but that gives us a lot of chance to barbecue. And we hike a lot with the lab, and that is really healthy way to do it. So this is a chapel. This is called Duke Chapel. We have this right in the center of the campus. Just in case you have never been there, it's about 300 feet high, and it's open for everybody, especially when you get your paper rejected or your grants rejected. It's a very good place to cry or mourn your papers. I do that a lot. Recently, especially. So, but on the happy side, we can also do weddings, and that's my two postdocs. And they got married inside the chapel. That's the inside. It's really beautiful, and you just have to reserve 2 years ahead. Otherwise, you won't get the chance to do it. So that means you have to keep your relationship at least for 2 years. That's a challenge. And we also have a lot of cats. Almost everybody has at least one cat, and we also have a few dogs, but mostly cats. And that's my cat, and Carl. He is really good at writing papers and grants. I mean, not getting grants, but writing grants, because he has been doing that with me for 10 years. And we also have some frog experts. That's my postdoc. Carlos on the left. He's not at Caltech. He's a professor at Caltech now. That's Jesse on the right. They are both frog biologists, and they catch frogs. And I'll show you some frog work we're doing. We also do some local frogs. So this is our North Carolina tree frog. And that guy's clearly calling his friend. That's Carlos and the two. They are doing field work for the frog.
The same one on the science journal?
No, this one is not magical enough. So we'll show you something else. But on the left, Carlos is doing his field work in South America, and that is the work we're doing. Okay, and we have a soccer team in the lab, and everybody plays soccer in addition to having a cat. Because we have this kind of tournament on campus, so you have to do half boys, half girls. But we don't have enough girls in the lab, so I have to borrow some family members to play. But we're doing great. We're second place last year. But the center guy, Luca, who is on the second row in the center, he just graduated. So I'm not sure how well we're doing this year. All right, okay. So with that, I just want to get back to science. Everybody in this room is well educated about light, and I guess we don't have to be convinced that light is wonderful, right? We are very rich. We have a lot of interactions between photons and tissues, and this almost give us all the information about the tissue's functional and molecular status. But that's a blessing. It's also a curse, right? So we cannot go very deep without losing the focusing. So that is the diffusion of the photons that limits a lot of imaging technologies within the first millimeter or so. And we have a competitor, right? So for ultrasound, they are not as rich as light in terms of tissue interactions, but for ultrasound is much better in terms of penetrating into tissue, right? So just in terms of sound wave penetration, they can go centimeters, tens of centimeters into the tissue without too much scattering. That's also a blessing and also a curse because they don't have too much features to extract from the functional side. The penetration is surely much better than light, and that's why when we are, amazed by how much information, how beautiful the optical images are, we also admire how ultrasound can penetrate, right? So this is on the left, that's a photoacoustic imaging of a placenta. We can look at all the microvasculature, all the functional status of the vessels. while on the right side is the ultrasound imaging of the baby, right? So you see the clear difference between the contrast and also the imaging depths in terms of their penetration. So we don't have to be jealous all the time. Actually, ultrasound can be useful. We can use them as our friend to do a better imaging, to do better treatment of disease, and also do better, even for better construction of the tissues, as we see later for printing. So this is the three major research directions we're doing at Duke. We build imaging systems for fundamental science. We use imaging for better treatment, and we also use ultrasound assisted printing for better, for better construction or better repairment of the tissue. So those are three directions. I cannot touch all the details. I will try to showcase some examples to demonstrate what we're doing in the lab. All right, so the first direction is the photoacoustic imaging. As you can see, that is my bread and butter. That was what I did when I was a student at Li Hong's lab, and still my major funding source to help us to build the lab. And for people who do not know photoacoustic imaging, you must know fluorescence imaging. So for fluorescence imaging, we get photon in, photon out through the radiative relaxation of the photon energy transition. If you do two photon imaging, you do the same, except that the absorption is two photon absorption. For photoacoustic imaging, it relies on physical phenomena called the photoacoustic effect. It is very, very similar to fluorescence. The first half is the same. So photons get absorbed, electrons get excited. Then when the electrons go back to the ground state, it doesn't release another photon. It actually goes through a long radiative relaxation channel, which is a photothermal channel, meaning the light is converted into heat, the temperature rise. And if we do that correctly, do that very, very quickly, that temperature rise can be converted into pressure rise and then the ultrasound emission. So that is the photoacoustic effect. You can see it is basically a energy converter. It converts optical energy into thermal energy, then into pressure, into ultrasound. So this seemingly really complex energy conversion process is, of course, it's very lousy. You lose all the energy along the way. Not very efficient, but efficient enough for us to pick up the ultrasound signals to look at the optical absorption at the beginning. So it is a energy conversion process happening inside the tissue. It's not like we're doing this light to sound conversion outside the tissue. Tissue itself is the conversion. So tissue converts light into sound, and the sound carries the information about the light absorption. So that's why I'm here speaking to you, because this is still optical process, and the signal, the ultrasound signal, eventually carries the information about which light is absorbed, where it's absorbed, and how much is absorbed at what wavelengths. So turning that physical phenomena into imaging, we use short laser pulse, typically nanosecond laser, and we get a little bit of temperature rise due to the photothermal effect. And then the pressure is released through the process, and we get ultrasound detection outside. So looking at the imaging process, you have two parts. The first part is optical excitation. And if the photons are absorbed by molecules, the molecules can give out your ultrasound signature, ultrasound signals. So if there's no optical absorption, there's no ultrasound, it's silent. So this process determines that what we see is the optical signature of the tissues, because it's very optically specific. And the second process is the ultrasound detection. Because ultrasound has this deeper penetration compared with light, the sound waves carry out the information about where the light is absorbed, which molecules absorb which light, and that information is carried out without too much scattering. So the ultrasound can get out of the tissue, very much reflect the origin of the signal without too much distortion unless you work in the brain. And that gives us the ultrasound determined resolution of the optical contrast. So that is the fundamental difference between us and ultrasound imaging, because the signal comes from the optical contrast, while the detection is from the ultrasound side. You will see many different examples. I'm going to give you why this kind of physical combination of light and sound can help us to do a better job in terms of the tissue imaging, especially beyond the first millimeter or so inside the tissue. Okay. And it's very flexible. So you have a chance to compare or to play with light and sound simultaneously. This is not enjoyed by other, for example, pure optical or pure ultrasound imaging. We can play with the light to focus the light into a small spot to give us optically determined resolution. So we call that optical resolution in photoacoustic microscopy. The resolution is on the micrometer level. The penetration is also limited by the light. So in that case, it's a millimeter or so, similar to optical microscopy, but this is the photoacoustic process. If you can relax the resolution to ultrasound determined, meaning that the light can be diffused, while we use ultrasound, especially at the high frequency ultrasound, to detect the optical absorption, then the resolution can be solely ultrasound determined to be tens of micrometer. In that case, the resolution is no longer optically determined. It's ultrasound determined. The penetration is also not optically determined. It's ultrasound determined. So you can go up to a few millimeter to a centimeter level because we're using high frequency ultrasound. So if you're not so keen about the resolution, you can let the light diffuse as much as possible. So we're getting into the diffusive region of the tissue while light is absorbed. The ultrasound in this case, generally speaking, is on a low frequency set. And we can use low frequency ultrasound for detection and then gives us the ultrasound determined resolution on the level of tens to hundreds of micrometer. The penetration, on the other hand, is determined by the diffuse light and how much light you can deliver, how deep you can deliver, and that is on the centimeter level. So looking through the different scales, photoacoustic imaging doesn't enjoy the high scalability from the cellular level all the way to tissue to organ level while using the same contrast. So you can study the same biological phenomena or biological process at the different scales by tuning your resolution versus the penetration depths on both light and sound configuration. So we are pretty flexible in terms of the resolution and penetration, depending on what you want to study. So put that into the context of the optical imaging. And photoacoustic doesn't enjoy the penetration depths, right? So we can go deeper because we can use the diffuse photons and we can still use ultrasound to determine the location of the light and also to go much deeper into the tissue, even is in the diffusive region. So that is why photoacoustic imaging can play a role in the very competitive optical imaging field because we are helped by the ultrasound in that case. What can we image? And a lot of contrast, a lot of molecules inside the tissue, they can be endogenously imaged, meaning that we don't have to label them to image them, right? So from the UV range all the way to near infrared, you have all those rich molecules which are strongly absorbing light, right? You can have DNA and RNA in the UV. You can have the hemoglobin in the visible light, near infrared. You have water, glucose, lipids, like collagen. They absorb in the longer wavelengths. So those molecules are there to be imaged. You don't have to label them. And the photoacoustic imaging can use them as an endogenous contrast. But like all of you, we love the near infrared the most because it can go deep. Right? That really highlight the penetration benefit of photoacoustic imaging because we just want light to be there. We don't care if the light is diffused or not. So if you use near infrared light as between 700 to 1300 nanometer, you can benefit from the highest penetration of photoacoustic imaging. So that's what we are doing mostly. And in addition to those endogenous contrast, of course, you can use exogenous contrast. You can use nanoparticle, organic dyes, genetically encoded proteins, as long as they absorb light. In other words, as long as they have colors, they can be imaged, right? So photoacoustic imaging, in some sense, is like a color sensor. So we sense different colors of the molecules because they all absorb different light. They have different absorption spectrum, and they tell us the spectrum through the ultrasound emission. All right, so this is just an example of what we can do with different endogenous contrast. For example, we can image the worms, the C. elegans. We look at the UV absorption. We can see the protein and the cell nuclei. We can look at some model zebrafish, right? We can look at their hemoglobin, look at their melanin, and for And for mouse, we can image the blood vessels, which is really easy for us to see because hemoglobin is so rich in the blood. And it's just so strong sometimes it's a problem. But now we can see the vessels without any labeling. If you tune the wavelength to longer wavelengths, for example, to the 1210 nanometer, you can get the lipids. You can also image collagen, water, depending on the wavelengths we're using. So this is the example that you can play with the optical wavelengths and see specifically what molecules you want to target. And that is not enjoyed by our friends in ultrasound imaging. So clearly, this is a optical contrast as we do photocosmology. You guys are doing your lunch, so I want to show you some lunch-related example. So this is a piece of bacon, and actually it's a beef bacon. So if you look at this one, not very healthy, by the way, a lot of fat and a lot of, some muscles, that's the collagen. And this is an example that we can use the near infrared light to differentiate different tissue components by scanning across different wavelengths. You can see how they respond in terms of different wavelengths, right? So it's the same piece of bacon, and we image them at a different wavelengths. You can see when the fat is absorbing, they send out a stronger ultrasound, while when the collagen is absorbing, they will do this as well. So by spectroscopically imaging the same piece of tissue, you can quantify how much fat this bacon has, how much collagen you have. So this is just an example of how we can do photoacoustic spectroscopy imaging by tuning the optical wavelengths and by looking at different tissue components, similar to spectrometer in optics. But the difference is that we can do this in deep tissue beyond the first millimeter or so. Okay, I think this is probably the most quantitatively studied bacon, right? We have been doing this as a phantom. And I'm going to show you a few examples about what photocosmology can do. The first example is a high-speed photoacoustic microscopy. This is on the superficial level. We focus light into tissue. We get the resolution on the micrometer level and the penetration on the millimeter level. And so why this is important? Because I'm really interested with the brain. So I do a lot of functional brain imaging, study different brain models, and we do this for our collaborators across the campus for stroke, for AD, for dementia. So we need a high-speed photocosmology to do the job to capture the functions. So this is and I don't want to get into detail, but this is a polygon-based photocosmology, and we can scan light very fast, and we can do ultrasound detection while the animal is sitting there, and we can do this with a very, very high speed across different wavelengths. So this is an example of photocosmology of the cortical vessels of the brain, and this is a mouse. And on the left side is a blood vessel map. And we can see all the vessels down to the capillaries without labeling. This is based on hemoglobin. And on the right side is more interesting. That is the oxygenation map of the brain. So photocosmology is a color sensor, as I mentioned. It can sense the difference between the oxyhemoglobin and deoxyhemoglobin in terms of their colors. And oxy is brighter and deoxy is darker. So that gives us enough difference to quantify how much oxygen is in the blood. So this gives us the oxygenation map in the vessel. And by doing that with a high speed, we're able to, for example, quantify the brain's response to epinephrine. Epinephrine is very often used in the clinics for treating cardiac arrest patients, right? So we spent 3 years on this drug, and we want to see how does the brain respond to this drug while under different age, under different conditions, different dose, right? Different cardiac arrest conditions. And just one example that this is a healthy brain. No disease condition, you can see the brain is responding to this drug very dramatically by reducing the oxygenation level, by constricting macrovessels. So once the drug is used, the brain is in the hypoxia condition, which is not good. We used to believe that brain is protected from the drug, but it seems that it's not. And because of this work, we have been contributing to the field, medical field, about how this very commonly used drug should be used, right? Or what's the dose they should be used on different populations, especially for aged population. And another interesting work I have been doing with this fast microscopy, as Sean mentioned, is just the very magic animal. We call that glass frog. So this frog, again, is not here. You don't have it. I don't have it. It's in South America. It's in the jungles. They are called glass frogs because when they are sleeping, they become transparent. And when they're not sleeping, they're not transparent. So this is really interesting. People know this for 100 years, but they just don't know how they become transparent when they're sleeping. Well, the purpose is quite clear. When they're sleeping, they can be transparent. They're invisible, so it's safer. But how do they do that is just a question, right? We don't know that. And photoacousticism kicks in. We can actually study this frog very well. I just want to show you the example of two images. One is when they're awake. So basically, when they're awake, they are normal. They're just like us. They have a lot of vessels. Actually, it's highly oxygenated. You probably don't know that the frogs can breathe through their skin, so they have more oxygen than us. And when they are sleeping, well, the story is very different. So they look different because they have a way to remove the red blood cells from their blood, 90% of the red blood cells from blood, and they concentrate all the red blood cells in the liver, which is the organ in the center. And the rest of the body is deprived of red blood cells. So they can do this 10 hours a day, every day, by staying basically bloodless for 10 hours a day. And by doing that, they are able to reduce their optical absorption by 3 to 4 times, and they are able to become 3 and 4 times more transparent. So that's why they can blend in into the surrounding, and they can be safer. And this is a little bit creepy. So we are monitoring their sleeping process. So you can see how they are falling asleep by removing their red blood cells from the blood. So you can see the blood vessels gradually become invisible. That's because they are removing the red blood cells. Okay, very, very magic. Well, the question is, how do they stay alive without red blood cells, which I don't really know, to be honest. And we suspect they are reducing their metabolism really a lot, and they also get the oxygen from the skin, so they don't need to use the red blood cells to do the oxygen transport. So that's just my suspicion. I don't really know what's the story. But more than just turning transparent, they are green, right? We all know that. How do they keep their green color is another question. Maybe we all know that most of frogs are green color. Some frogs are not for protection purpose, but why are they green? So this has been a question people have been asking, right? Frogs are not like trees or leaves. They can express the pigments which are green color. It's actually very, very challenging for animals to be green. If you think around the animals you see, very few of them are green because green color is quite difficult to make. And they don't really have those pigments in their skin to do it. So we found out that they actually do this through a mixture of 2 different pigments. So they actually have a yellow pigment called halogen, which is more or less yellow color. And they have another very unique pigment, is blue color, called BBS, biliverdin binding serapin. So by doing that, they are able to absorb light both in the blue range and also the red range. So basically, they absorb 2 bandwidths or 2 ranges of light in the blue and red. So you know that if you mix yellow and blue when you paint, you get green. So basically, that's how they become green color, because they have 2 different pigments in them. So they are a good painter to begin with. They know how to do green color by mix yellow and blue, right? So that's also photoacousticism's contribution to this really interesting animal. And we also found out that it's a recent work is that they are so scared of blue light, although they have blue pigments in their brain, in their skin. And so we are studying this frog. We found out that they are really, really scared of blue light. So when they're sleeping, you shine blue light on them, they wake up and they try to move around and get away from the blue light. And on the photoacousticism side, you can see they actually pump more blood into the body to become active. And this is really something they are scared of. And we try to use different colors. We shine green light, we shine red light. they don't care. They sleep sound. They don't really like blue light. And we still don't know what's the reason. But we are trying to figure out what is in their skin, why do they don't like blue light. And it seems that they have some opsin channels in their skin that is more sensitive to blue light. We'll find out more as we do more research on this. Okay, so this is just some examples about this animal. But my point is that this is possible. I mean, this kind of research is possible because we have this high-speed, high-resolution, broad field of view photoacoustic microscopy, and we do not have to label the blood. If we have to label the blood cells, all the research is impossible because those frogs, they are so fragile, they don't like any labeling. So we can do this work by photoacoustic imaging without labeling. That is a really important feature of the technology. And another important organ we want to study is placenta, which is also quite difficult to study because they are so dynamic. They are changing all the time, and they are evolving really fast over the pregnancy. And there's also deep into tissue, and this very sensitive to motion artifacts. So those kind of target is a nightmare, right, to study, especially when you're doing high-speed, high-resolution imaging. So we have been able to do that over the last few years because of the imaging technology has been evolved so fast. And we're able to, for example, monitor the same placenta over the whole pregnancy of the mouse, 20 days actually. You can see how the vessels evolve, how the microvessels remodels, how the oxygenation change over time. And this is a healthy, normal pregnancy. So you can see over the 20 days of time, the animals becomes more and more oxygenated. I mean, the placenta is more and more oxygenated, which is normal because at the very beginning of the placenta development or a very early stage of pregnancy, the placenta has hypoxia. It's almost like a tumor to the body. So they want to stay in the hypoxic condition so they can trigger the angiogenesis process to develop a lot of vessels to grab the oxygen nutrients for the fetus. So they have to be hypoxia to begin with to develop vessels. So that's normal. And I want to show you that when they're not normal, what happens, right? The first example is when we are looking at the animal over 24 hours. So we can do this over 24 hours of time and see how the placenta gradually establish different zones. In this particular case, we're looking at this decidual zone, that's the buffer between the mom and the fetus. You can see how the vessels are evolving over 24 hours and how do they change their oxygenation map over the time. And another example is how they are responding to heat. So there are a lot of extreme heating days, right, nowadays because of that global temperature rise. So we are able to study a heat exposed animal model, and we see how the pregnancy responded to heat. You can see that at the beginning it's normal, the placenta normal. As we increase the temperature over the 30 minutes of challenging time, you can see the placenta becomes hypoxic. So the maternal system actually protects their own organs, while placenta is considered as a secondary organ. So basically they move the blood from the placenta and to support other organs. So that's why if this is a human, when we say that is a problem, right? So anyway, so this is possible because we can do those kind of imaging with high speed, high resolution, and more important, the functional information. So we can monitor the process with all those functional measurements. And so we move on to humans, right? It's really challenging to do, but we're able to overcome some technical hurdles, and we try to do this on humans as well. So this is a preliminary study. We are working on pregnant women at different pregnancy stage. And because this is solely non-invasive and we can do this over time, and this is a typical ultrasound image of the placenta. You don't see much because the placenta is basically a bag of blood with some vessels. It doesn't have really a lot of features for ultrasound imaging to see. So if you look at the ultrasound B mode, it's basically just a featureless structure. And because ultrasound can go really deep, we can get to 8 centimeters. That's not a problem, as I mentioned. And for humans, we are able to see the blood vessels at a different gestation stage, right? So you can see at 16 weeks, it's early pregnancy versus 33 weeks, you can see the placenta vessels. And so that is ongoing work. We're trying to compare the early stage pregnancy, late stage pregnancy, how does the vessels evolve, how does the macro vessels remodel, and how they change their perfusion pattern to feed the fetus at a different stage. This is ongoing work. And on top of that, as I mentioned, photoacoustic imaging can be a friend with ultrasound. So we are doing more and more ultrasound together with photoacoustic imaging. This is one example. We can combine photoacoustic imaging with ultrasound, particularly with ultrasound localization microscopy. In case you don't know that, this is a technology that's very much like a storm or PAM in your super resolution imaging. So we can track the labels, ultrasound labels inside blood vessel. Those are small dots, moving, this flowing dots. They are microbubbles filled with gas, micrometer level size. And when we use ultrasound to track them, you can see how they move inside the vessels. Its diffraction limit is resolution not terribly good, but as your ultrasound localization microscopy, as your storm, we can do the same trick. We can actually clean up the image by localizing the bubble centers. So we can actually do resolution enhancement by tracking the centroids of the bubbles and cleaning up the image by a few times without, again, without hardware change. And this is just examples that we can improve resolution by ultrasound localization microscopy. Why this is useful? Because with this, we can do a few things that photoacoustic imaging cannot do. For example, we can quantify blood vessel blood flow speed by tracking the microvessels, and we can quantify the blood perfusion as well on top of photoacoustic imaging. Okay, one example why do we do this is we try to study galactic system, and this is something that's well studied in for example in aging, in stroke, and people try to connect galactic system with neurodegenerative disease. For example, AD, right? We understand that if you have a slowed down galactic system, which is the garbage clearance system inside the brain, if you do that, you will have accumulated garbage, right? All those kind of metabolic waste is not cleared out through the brain in a timely manner. So you start to have clogged vessels, clogged brain, the amyloids, right? So those are the byproducts of metabolism. So galactic system is like your every week you have your garbage truck circulating around the neighborhood to clear all the trash, and galactic system does that. Typically, people do this galactic imaging using fluorescence microscopy, so they can trace the fluorescent label throughout the brain and look at how the galactic system is moving the fluorescent tracers around. And the problem is that you cannot do very deep. Most likely you can do this on the brain surface, but you don't really know what's happening inside the brain. It's a three-dimensional system. So photoacoustic imaging can help by tracing a non-fluorescent tracer, but optically absorbing. So we have studied two examples: a young brain with intact galactic system, and an aged brain with impaired galactic system. You will see how strikingly different they are. So the first example is on the top, that's the young brain. You can see how does the photoacoustic tracer, which is the color, the yellow-red color, is circulating throughout the brain within 40 minutes. So basically, it's like a marathon, a very fast marathon. So from the beginning, it's the back of the brain and circulating the whole galactic system throughout the neighborhood within 40 minutes. So basically, it's a one round of galactic flow. It's 40 minutes. And you look at the aged brain, which is on the bottom, you can see how slow they are. So the galactic system actually takes much longer time to move those tracers around, and within 40 minutes, it doesn't even finish half of the race. So basically, that is how slow, how clogged the system is. And you can imagine this is happening to the aged brain that will slow down the metabolic waste clearance that will cause many issues, right? And we are working on different animal models. With this technology, we're studying how stroke changes the galactic system. And clearly, right, the galactic system is partially driven by the vascular, we call that peravascular space, driven by the arterial vessel pulsation. So if the vessels are not perfused well, they cannot drive the glymphatic system well. And the other example is how does sleep helps us. So I don't know how many of you sleep 7 hours a day, which is recommended, right? But if you do not sleep well, how does that change the brain's metabolic waste clearance? And I can tell you that you need 7 hours of sleep that help you to stay sane, right? So, all right, so we are able to combine photoacoustic imaging with molecular probes as well, right? So this is a genetically modified protein that can be photo switched between two different states. So we do this together with ultrasound. We can see how does the neurons can be labeled genetically, how does the tumor cell can be labeled genetically. So we can do something similar to fluorescent imaging on the genetically encoded cells, but in this case, at a much deeper penetration depth. Just two examples of how we do this. Okay, so that is roughly my first topic is photoacoustic imaging. I guess my message is that ultrasound is not an enemy, right? We can use ultrasound to help us to go deeper, to see more clearly, and to give us more functions that light cannot do. My second topic is very similar to the first one, but is on the clinical side. And I have the fortune to work with over collaborators at the Duke Urology. And this is the technology they use to treat kidney stones. It's called the laser. It's called laser lithotripsy, LL in short. About 10% of the population will get kidney stone eventually. So I guess we'll have a few people in this room will get kidney stone by statistics. So if you go to hospital, this is the treatment you will likely receive. Is the urologist will send a fiber into your kidney through a uroscope. So that is, they can say it, just like the picture in the middle, they can say it, and they will pump short laser pulse to the stone and blast the stone surface very, very violently. So basically you can see how they actually use laser pulse to blast the stone piece by piece, layer by layer, and actually to treat the stone, break it into small pieces, and so they can get a stone-free condition, right? So that is what they do. And you may want to say, how does that work? Is that because the light is absorbed and the photothermal effect ablate the stone? Not really. You may be wrong. You guessed wrong. So what really happens is the cavitation. So the light is not absorbed by the stone. That is actually absorbed by the water around the fiber. So when the water is heated up so hot, they generate a bubble. When the bubble bursts, they send out the shock waves, which is so strong that actually shatter the stone surface layer by layer, piece by piece, and that gives you the treatment effect. Okay, so it's not direct absorption, light absorption by the stone, but it's by the liquid around it. So as you can see, the therapeutic process is not done by the light directly, it's done by the shock wave, which is through a cavitation process. When people work with laser cavitation, you probably know that really well. So this is a treatment that they are using. And the problem is that when the surgeons are doing the treatment, they can see the fiber, they can see the stone, but they cannot see the cavitation. They cannot see the shock wave. So that is something they cannot control, and that is very important for them to do a good job because shock wave or cavitation is a determining factor of how efficient the treatment is. It can last for hours or minutes, depending on how good the surgeons are. So we can kick in this process by harvesting or to listening to the ultrasound signals or shock wave signals, which is used to treat the stone, while the same shock wave, they're not just going to the stone, they're also going to the tissue surface, and that is a free lunch we can pick up. So we use ultrasound transducer to pick up the signals, and we can reconstruct where the sound waves coming from, and that means where the cavitations are happening, and we can also quantify how many bubbles are generating, where they are, when do they burst, are they close to the stone surface, are they strong enough to ablate the stone, and that's all the quantitative information we can gather as a free lunch without changing the treatment pipeline. So this is actually 3D ultrasound, 3D cavitation mapping. It's like a 3D map of the cavitation signals. You can imagine this like a group of bubbles around the fiber, close to a stone surface, how they are bursting and treat the stone as the treatment goes, right? So we are pretty happy with this because now we have first time to see the three-dimensional map of the bubbles around the stone surface, and we can give this to the surgeons to say, hey, you are doing a good job or not. since we're all nerds, we are not happy with the resolution. So we look at this image, and we think this is actually very similar to the bubble imaging we're doing for the ultrasound, because eventually the signals come from the bubble bursting. So the bubbles are bursting and send out the shock waves to treat the stone. And those bubbles are so small, they are point sources for ultrasound. Since they are point sources, we can treat them as a point target, and then we can track their locations, again, the center of the locations. So we can improve resolution by tracking the centers of the ultrasound, the bubble signals, and then we can improve resolution by more than 10 times, actually. So we can localize each bubble individually with a resolution about 30 to 40 micrometers. It's 10 times better than the diffraction of the ultrasound. So we can specifically study or investigate or look at or grade each bubble individually. Instead of giving the whole class the same grade, like C+, now we can grade each student, each bubble individually. See which bubble is doing a good job, which bubble is actually not useful. So now we can provide a real-time guidance to the surgeon, like my collaborator Dr. Lipkin in the OR. So instead of just looking at the videos which he has from the the endoscope, and he can see the fiber, he can see the stone, he cannot see the cavitation, or he cannot see the bubbles, and now we can tell him, hey, buddy, you're doing a good job because you are generating all those cavitations. You are generating strong treatment efficiency because all the bubbles are distributed close to the stone surface, or they are big enough, or they generate enough bubble density that gives you the best treatment efficiency. So now this is real time. We can tell the surgeon where the bubbles are, how close they are. In the background is the ultrasound image of the stone, and on the foreground, that's the color is basically the cavitations as they treat the stone. So eventually, what we want to do is, we're not there yet, is we can grade each bubble or each treatment, each laser pulse, based on its cavitation efficiency. So we can tell the surgeons in real time, where are the bubbles? Are you doing a good job? What's the heating rate of your bubble or your laser pulse? Are you too far, too close? Are you doing a efficient treatment or not? As a closed loop system, so they can adjust their treatment in real time. Okay, so that is ultrasound-assisted treatment for laser trypsy on kidney stones. As you can see that this is actually not so far away from photoacoustic because the sound wave is also generated by light. It's just not a photoacoustic effect. It's laser cavitation. So it's laser-induced cavitation, but the whole process is almost the same as the photoacoustic because we still listen to the ultrasound through the optical process, and we can localize where the sound waves are from, and we can improve resolution by localizing the bubble centers, and we can provide a real-time image. And luckily, this process has a much, much better SNR. Because the photoacoustic imaging is not so efficient, the signal is not so strong, but for the cavitation mapping, it's so bright. It's like so bright, you cannot ignore it because the shock wave or ultrasound signal, ultrasound pressure is strong enough to burst the stone. You can see that's very, very strong ultrasound. So we pick this up almost like a free lunch. Okay, so I have a few minutes left. I'm going to jump to the next topic, which I promise you is on the treatment on the tissue building side. So I know this is a really broad topic because bioprinting is a big field. People use all kinds of printing technology, all kinds of ink composition or ink formula to improve their efficiency of the polymer cross-link to do bioprinting with cells, without cells, with scaffolds, right? So that's a big field for printing. However, as the optical imaging people, the bioprinting community also suffers from the limited penetration. So when they do the printing with the laser, they also limit the penetration to the first millimeter or so, or even just on the skin surface. So they are not able to go into the tissue and do printing organs, printing tissues, printing the damaged structures with their ink. Even the ink can be injected or can be delivered by catheter, but the light doesn't go in. So we're thinking, can we do this with ultrasound? again, ultrasound is a friend, right? So we can use ultrasound to do printing if the ink is sensitive or responsive to the ultrasound waves. So we developed with my collaborator Shrek Zhang at Harvard School of Medicine. So we are able to develop a family of inks, we call that resins or inks, that's sensitive to ultrasound waves. So when you expose the ink to the ultrasound, especially with high intensity ultrasound, the temperature change due to the ultrasound absorption will change the ink's viscosity and also their phase. So basically they are turning from a liquid format, liquid phase into a solid phase, that's printing. And if you can pattern your ultrasound waves in a high precision way, you can actually pattern in the printing accordingly. So that's the ultrasound enabled printing. We call that deep tissue acoustic printing. So this is an example of what we can do. I specifically choose the ink that is a red color because the traditional optical printing will not be able to do this because the light is so absorbed. But for ultrasound, it's okay, right? You can print in a ink tank. You see there's an ultrasound transducer at the bottom. That's the silver metal part. That's the ultrasound transducer. And you can print a vessel structure, right? That's all you want. You can do that with different resolution. You can also print through tissue. That is a benefit of doing ultrasound. You can through tissue, through skin, through fat layers, through the muscles. So you can get a different structures printed. For example, you can also print three-dimensional structures. So you can print a tube like a blood vessel, or you can print a ducky. Right? So that is a 3D, not so beautiful, but you get the shape. And what is the application? We have a few demos. We're doing this on the bone fractures. We can print inside the bone to help the bone fracture repairment, and we can also print in the tumor to help the chemo drug delivery. So we actually print around. We can print around the tumor. We can print inside the tumor, and we can integrate the chemotherapy drug into the ink so we can have a slow release. And recently I've been working on heart, so we can print inside the heart to fix, we call that atrial appendage closure. So it's a surgery that have to close a hole in the heart. So we're doing that with ultrasound printing. So hopefully we're able to do this without opening the chest. All right, so this is very short, but I think this is another example of ultrasound can help us to do a better job. And essentially, that's my message, right? I want to say that light and sound can be friends. And don't be scared of ultrasound. They are quite useful. And photoacoustic imaging is one example about ultrasound enhanced imaging, right? We can do deeper imaging with ultrasound detection. For cavitation mapping, we're using ultrasound as an indicator of the therapy efficiency. And lastly, ultrasound can help us to go deeper through a skin surface to build structures inside the tissue. So it's like imaging, treating, and building tissues and depths. All right, thank you very much for your time, and I'm happy to answer any questions. Thank you.
Okay, we have 5 minutes for questions. Oh, a lot.
Thank you very much. As a clinician, I have to say that it is amazing.
Thank you.
There are certain conditions in life, in disease, such as Alzheimer's in the elderly, or endometriosis in young women, or during the reproductive age, that they're still waiting for many years to a proper diagnosis in order to improve early detection and treatment accordingly. Do you have something like that in the pipeline?
For, I'm sorry, for what kind of?
Either for Alzheimer's disease,
disease
in the elderly, or endometriosis in young women. Endometriosis, as you may know, is a condition in which the inner lining of the uterus is spreading around. It is benign, but it can spread all over the body. And early detection is very important. The changes that you've shown with a decidua, which for those who aren't familiar with the decidual changes are the endometrium during pregnancy.
Yes.
So this is so impressive. So it takes me to this question in which early detection of endometrial lining outside the uterus is something that can help many women. It's about 1 out of 10 women who suffer from that. can lead to a better treatment.
Well, first, thank you for coming. You know, we always want to work with the clinicians, and you guys are the reason why we work hard, right? And I want to say that, you know, I actually don't know. It's not because I'm not interested. It's really because the technology is so new. And when I show my images of the placenta, human placenta, to my clinical collaborator, she's equally amazed. She's like, wow, this is just the best image I've ever seen. And I cannot do this with just regular ultrasound or Doppler ultrasound. But she doesn't have any idea what she's looking at. And because there's no baseline, you know, this kind of image is kind of new for everybody. And then my answer is that we need to build up the baseline, the foundation first to let the clinicians like you to understand what you are seeing as a normal condition. Then we will be able to look at what is a diseased condition, how the difference can tell us either it's early stage or what other conditions we may see there. So my short answer is I don't know. I need to work with clinicians like you to figure out how or if we can do this.
I'm not expert in Alzheimer's, but in women's health, I will be able to collaborate with you and give you some further information in order to work that, because put that in your agenda, it's important.
I'm allowed to do that. Yeah, it's sometimes we do have these challenges that we are so excited about the imaging, the technologies, and but the physicians and the doctors, they have no idea why we're so happy, right? So they don't see the connection between the imaging and the disease diagnosis.
Great talk. I have
guess
a
he's more
question on
senior,
your
yeah.
laser ablation. And for the super resolution to work, you have to assume that when you have a focused beam, you only generate a single bubble at a time. Is this always the case when you have that treatment for that cavity generate?
You don't. So when I think about this, I almost feel like it's unreal, because how do you get this kind of strong signals without any background, and all the signals are points, and you don't even have to do anything different from a traditional ultrasound image, is a target ultrasound transducer there. So back to your question, all those bubbles, a single laser pulse can generate up to, I think, maybe 10, 20 bubbles. So it's not a single bubble. The light is absorbed, it generates a huge bubble to begin with. And when the bubble collapses, they collapse into many small satellite bubbles. We call the secondary bubbles. They are very small, but those bubbles are the reason why the stones are treated, because they are so spread out. And they are on the stone surface, they actually blast the stone surface and generate those kind of small craters. So that is the reason why the treatment can be so efficient if you control the cavitation correctly. So back to your question, if there are like more than one bubble, can we still do that? That is another really lucky thing we have, because those bubbles are not bursting at the same time. So even they can be spatially overlapping, but they are bursting at a sequential kind of pattern. This bubble burst first. The second bubble, although it's overlapping spatially, but it's bursting at different time points. So you just have to listen, just like listen to your music. There are like notes. You can say they're like note 1, note 2, note 3. Each bubble is a note, and they are singing a song, but they are happening at different times. So by just looking at the time trace, this is a beauty of ultrasound, because it's so slow, and you can clearly see which bubble is bursting at what time point. And so you can just focus on that single bubble. But in a rare case that you have two bubbles, which are spatially so close, which are also bursting at the same time, you're in trouble. So basically, you cannot differentiate those two. But these are rare conditions, rare events, and I don't think the doctors care too much about those kind of rare events. Yeah. So it's just a good condition to use the imaging. Yeah.
Thank you for the great talk. I have many
Thank you.
questions, but I'll focus on my main one, which is in your human studies, what is the imaging depth that you've been able to achieve and what is the maximum resolution that you've gotten at that depth?
Great question. So for the human study, surely we cannot go too deep because for half of the women, their placenta is in the front. We call that, it's in the front of the uterus. And so that is about 5 to 7 centimeter. Depends on the body weight. I mean, so some are deeper, some are shallower, but on average is about 5 to 7. And those kind of placentas are accessible because we can go deep enough. For the other half of patients, who have the placenta on the back, not really on the back of the uterus. So those placentas are about 10 to 15 centimeters. We're out of luck. We cannot see them. So there are, some channels, some kind of when people use that for ultrasound imaging, they go through the side, the waist, and they see it from the side. And it's closer to the deeper placenta, but we haven't got lucky enough to do that. We don't really have good results on that. But mostly, if it's on the front, the 50% of the women who are imageable, so we do that for those patients. In terms of resolution, it's ultrasound resolution is about 300 micrometer. So that's purely ultrasound. We use a 3 megahertz ultrasound. It's about 300, 400 micrometer resolution. Yeah.
Do we have any question from online? Michelle, do you have a?
Yes, there is a question.
Okay.
It says, very cool research. Could you comment on the miniaturization of photoacoustic imaging device? What is the most challenging part?
Oh, that's a good question. I think people are doing endoscopy, photoacoustic imaging, photoacoustic endoscopy. The challenging part is the combination of light and sound. I know Zhongping has been working on that. And if you just do optical endoscope, it's just optics. If you do ultrasound endoscope, it's just ultrasound. But when you're trying to do photoacoustic endoscopy, you have to do both light and sound. So to miniaturize the probe with both optical components and the ultrasound components is a challenge. And so that is the most challenging part. And when people are doing pure optical photoacoustic imaging, like use both light to excite the signal and also use light to detect the signal. So that kind of design, like all optical detection is more spatially friendly, so we can actually do a better job with that. So the challenge is how to combine light and sound together in such a tiny probe. And so that is the most challenging part of the photoacoustic endoscopy.
Okay, we can have 2 more questions maybe.
Thank you for an amazing talk.
Thank you.
So my question is regarding the cavitation. So how do you, is there a cavitation threshold based on the absorbed fluence or the temperature, spatiotemporal gradient? Because if in photoacoustic imaging, you don't want the cavitation happening because that would interfere with the photoacoustic signal.
Yeah.
So what is the cavitation threshold? What quantities define that there will be cavitation happening?
So you are asking about the cavitation mapping technology, right? So in that work, there's no photoacoustic imaging involved. So it's purely ultrasound. It's just the light is absorbed by the water and generate bubbles, and bubble burst generate ultrasound, and we can detect that. And so, as I said, it's the efficiency of the detection is quite high because there's no background, and your body doesn't generate ultrasound naturally. So there's no ultrasound as a background. So once you listen to the cavitation signals, everything is signal. And because it's shock wave essentially, and the shock waves is on the level of hundreds of kilopascal, hundreds of pascal, even up to kilopascal, even megapascal. So the signal is very strong. And the reason we do have some threshold because for some tiny bubbles, when they are bursting, their signals are also very weak. But those kind of bubbles are kind of irrelevant because those bubbles are not generating strong enough pressure to burst the stone. So those are useless bubbles, and we don't really listen to them. And as long as the bubbles are strong enough, they are therapeutically effect. Those signals are typically detectable even at a like 10 centimeter penetration depth because the kidney is pretty deep and it's 10 centimeter. So as I just told Zhengping that it's very lucky for us to have such a strong ultrasound pressure to begin with as a therapeutic tool. Then the imaging side is just like we're picking up the leftover of the therapeutic pressure, and that's already strong enough to detect. Yeah, I still cannot find any like downside of this technology. Every time I talk about it, my heart rate is going up because I think this is just a once a lifetime work. Really, really amazing for treatment monitoring.
Thank you.
Thank you.
Is the literature see laser also pulsed? And what duration?
It's pulse laser. It's on the hundreds of microsecond level because they have to build up enough photons to burst it up to generate a big bubble. If it's too short, then the problem is the bubble is not strong enough. So there's hundreds of micrometer. It's amazing. You can see that the light is emitted from the fiber tip, and the bubble is growing as the light is continuously emitting within the 100 microsecond window. Because the light cannot pass through the bubble water interface because the water is so absorbing, the light is completely absorbed at the bubble water interface. So that kind of strong absorption of light keeps pushing the bubble to grow till the moment that the bubble is too big, kind of hold itself, or the heating process is over. So that's actually why they have to use a longer pulse to keep growing the bubble to a certain size. And the bubble burst, generate strong enough signals to create the stone damage. Yeah.
Okay, that's all. So, let's thank Dr. Yao again.
Okay, thank you very much.